viewed as being some kind of intelligence that is taking a essentially potentially unstable system and adding enough smarts so that it makes it stable. Okay. It's a classic example of this, and we will not study this, but by the end of this chapter you kind of have enough maths to understand what to do, though you won't actually study it. This is the classic example of a control system which in some science museum you'll see it. This is a cart, and on the cart there is a stick, and on the stick there is a weight on the top of the stick, and the stick is just resting like this. It's called an inverted pendulum. Okay, it's an inverted pendulum. And there's a control system which can move the cart either forward or backward, that's all, right? So it's like balancing a stick on your hand, right? So the system is inherently unstable, right? If you were to leave it, the smallest breeze will cause it to fall over. But the control system is going to make it stable. It's going to stay up. It's not going to fall down. Right? Same thing, you have a broomstick on your hand, I'm sure all of you have done it as a kid, try to balance a broomstick on your hand, like so. It's an inverted pendulum, and you kind of intuitively know what to do. If it's falling over like this, you move your hand like that. If it's falling over like that, you move your hand over here. And the equilibrium point is just exactly center, but it never stays at equilibrium. There's always a disturbance, and you kind of keep moving your hand, but it stays up. So that's what the controller is doing. The controller is sitting there, kind of moving its hand, moving the system in such a way so that all the disturbances are accommodated for. Okay, and the thing doesn't fall down. If for those of you who fly, you'll be either pleased or terrified to know that most planes today cannot fly, on their own, without a control system. Actually, thousands of control systems. Without these control systems, the plane is basically unflyable, especially military jets and so on, which travel much faster than speed of sound. There's no way that you could fly it yourself. There's this notion of fly-by-wire. Fly-by-wire means that there's these control systems which are doing all the work of flying for you, and there's absolutely, if any of the system goes down, there is absolutely no way you're going to. Basically, it's a flying piece of rock, something. And if any systems fail, you're going to just plummet to the earth because it can't stay up. Either you should be pleased with the use of mathematics in making you fly faster than the speed of sound, or you should be really worried that somebody made a programming mistake. You imagine getting a blue screen of death on your controller. Okay, so any questions about this? Okay. I want to really emphasize this because quite often, especially if you read texts on control theory, textbooks on control theory, it jumps straight into the math. It jumps straight into like, okay, here's a modular system, here's x, here's y, here's u, here's r, da da da, and then let's go and do our transforms and here get all these equations. Fine, but there's something behind all this. There's actually a real system behind all of this, and how do you get from the real system to the model? And second, what does it all mean is left out. And what I'm trying to get you to do is to understand intuitively. So if you remember that broomstick balancing on your hand as an example of a control system, you really get what's going on. How responsive should it be? It's falling over. Do you want to jerk your hand or do you want to move it back? Right? And that's example of responsiveness. What does stability mean? Well, it shouldn't fall over. That's stability. It's instability when it falls over. So these kinds of intuitive understandings of control systems are very important if you're trying to use control theory, because you can get lost in the math very easily, and in the end you may get something which looks reasonable but it may actually be completely wrong. So guiding your ideas through intuition is important. Okay, going to now switch gears and spend some time on this on a web server. And I chose a web server because it's sort of a classical example of actually a queuing system. So the same exact thing can be used for any queuing system. I'm not actually covering queuing theory here, but if you were to study queuing theory, you would recognize right away that this is a sort of a standard queue. So I'm kind of giving you a little bit of queuing theory on the side, I guess. And certainly you should understand this because it's true for any queuing system. Web server or Tim Hortons, in Davis Center, they all have the same behavior. So let's look at how we would look at a typical queue, and then the modeling of the queue or the web server using control theory. So the first thing I want to do is to show you a very, very important picture, which kind of is an X-ray into any queuing system with discrete arrivals and departures. Okay, discrete arrivals and departures meaning that, you know, like an integer number of occupants at any point in time. So this is time over here, and what we have is let's, for purposes of simplicity, we'll assume time is discrete, though actually time can be continuous. But and also we'll assume that the number of occupants in the queue is discrete. Okay, so it's either one person in the queue, 2 or 3 or 4. You don't have 1.5 people in the queue. Okay, so in this case we actually are looking at a request to a web server. It's on people, and what you're looking at is arrivals and departures of web requests to a web server. So how does a web server work? So let's say you're running an Apache web server on a system. What you do is you listen on port 80, and you're listening there for you have to listen. The system call and it says listen, and then somebody from somewhere is going to do a connect call to your IP address, and you get a message saying, hey, somebody tried to connect to you, and you say accept. Okay, and you say accept, you get handed off a different port number, and you get a connection opened up. But let's say you're sitting there and your Apache server is sitting there, and suddenly your website is on /dot, so you get lots of connections. So you do accept, and by the time you say accept, 3 more people have tried to connect to you. What Apache does, and what all web servers do, is to have a limit on the number of open connections. Okay, the limit is typically set to, I don't know, 20 or something like that, and that's a default configuration parameter. But it doesn't matter. Let's say it's 20, so you're going to have 20 connections open. You accept all of them. When the 21st request comes in, you can't accept because all your threads are attached to the different connections. And so what happens is that the incoming connection request is going to be put into a queue. It's going to be sitting there waiting. Okay. Now, actually, a couple of things. One alternative is for your web server to say, I'm busy. Okay, I don't want to deal with you. Just go away. And that's your I forget what it is, 500 server busy. Try again, something like that in HTTP. But let's say it's not, then it will be put into a queue, and when you finish processing one request, then your thread frees up and you can do another accept, and then the queue goes down. Okay, so just to make life simple, let's assume that we have a system where there's only one thread, there's only one connection can accept it. So the thread is sitting there, it receives a connect request, it accepts it, and then goes does the thing, and then it comes back, okay, another request. So what we have is, let's say at different points in time, we have arrivals, and we'll assume that if you have 2 or 3 requests happening at the same time, we'll view them, if they're happening in this time, and we'll just batch them up and say, let's say you have 1, 2, you have 3 arrivals at time, this is time 1, time 2. So at time 2, we have 3 arrivals. What's really going on is that between time 1 and 2, we had 3 arrivals, okay? And then we had, let's say, at time 5, we had some arrival, and then we had no arrivals here, and then okay, so that's all we have over here. So this is arrival number 1, arrival 2, arrival 3, arrival 4, arrival 5, and arrival 6. Okay, so how do we read this? At time 1, there's 1 arrival. At time 2, or between times 1 and 2, there were 3 more arrivals. At time 3, there were 2 more arrivals, and there were no arrivals after that. Okay, and so this curve over here is obviously called the arrival curve, and it tells you when things arrive. You can look at this curve, you know exactly how things arrive. Okay, if you were to draw sort of the, if you were to draw this, there would be 1 arrival here, there would be 3 arrivals, 1, 2, 3 arrivals here, and there'd be 2 arrivals over here, and then none afterwards. So that's a cumulative of this density graph over here. So it's a discrete density function, and that's a cumulative, and that's the arrival curve. Okay. The other curve that's important is the service curve. So when do things get served? Let's look at the time period between 0 and 1. Okay, there were no arrivals in the system. System had nothing to do. So nobody sent the server any web requests. So obviously you couldn't serve anything. There was nothing to do, right? When the first arrival happens at this point, okay, that's when you can start service. So the service curve is going to be matching the arrival curve over here, and let's say that takes 2 time slots to serve it. So it takes this time to serve it, okay, and then what happens is it serves the next one over here. So 2 gets served over here, that takes 2 slots to serve, and then you get a bunch of teeny requests. So in the next time instant at 5, you're able to serve, let's say 1, 2, 3, and then you have one over here and then one over there. So this one over here, this lower one, and I really wish I brought my colors here, and I'll just make it darker. This darker curve is called the service curve. And as you can see, the service curve is always going to be below the arrival curve because you can't serve something that isn't there, right? And what we're saying over here is that, we're basically telling you how long it took to serve every request, or at least it tells you between, so this first request took 2 time slots to serve, the second request took 2 time slots to serve. These 2 requests got served here, but all these guys were served in 1 slot, and then the last one took 1 slot to serve. So you kind of know how long it took to serve each request, and that's the service curve. And you can define exactly the same thing for any discrete queue. So if you go past the Tim Hortons, you can easily see that these are arrivals of customers, these are service curves, and here's arrival and service curves looking like this. Okay. And any questions about this? Okay, so now we get the very interesting result, which is the horizontal distance between the arrival and the service curve, and the vertical distance and the arrival and service curve. So let's look at this horizontal distance like this. So if you look at request number, if you look at this request number 2, okay, request number 2 arrived at time, take it back. Let's say this request number 2, it arrived at time 2, okay, because that's why we had this over here, and it got served at time 5. Right? So this distance is sort of the time it spent in the queue. Okay? It arrived here and left there. So it spent that much time. 3 came here, it spent this much time. 4 arrived here and spent this much time. 5 arrived here and got served over there. So this distance is the queuing delay of that request. By just looking at the horizontal distance over there, I can tell you what the queuing delay was. Okay? We have to adopt the convention, obviously, that we have to go all the way to the furthest end. So we start from here, and this is the time that it got served. And that's the queuing delay. So we'll just write that as delay. And if you look at the vertical distance like this, the vertical distance at any point in time, what does it mean? So let's look at this. So we've already got 6 arrivals, but we only served 2 at this point. So this must be the queue length at that point in time. Right, so the vertical distance is the queue length. Okay, and that's kind of a nice thing, because you can look at these 2 curves now and just say the maximum vertical distance is the maximum queue length, and the maximum horizontal gap is going to be the maximum queuing delay. And so we can just look at these 2 arrival and service curves and actually compute these quantities of queuing delay and queuing delay and queue length. So we can say the delay experienced by any request we can find out from these 2 curves, and we can find the queue length at any point in time. Okay, and a bunch of things we do in queuing theory actually relate to these curves and the ability to mathematically bound the gap between these curves. Okay, and this is a huge area of work called network calculus and stochastic network calculus, where we study these things in great length. Now, to simplify this, so the thing is, this is discrete. In discrete quantities, we often have edge cases, and we have to worry about, do I count this or do I count that? What's happening in that, instantaneous time instant? We have these discontinuities, and it's messy. Okay, discontinuities and discrete things are always messy. So, one thing we can do is to pretend that arrivals happen very, very fast and service happens very, very fast, which is sort of true for web servers today, right? We can big websites like Amazon and so on typically get thousands of requests every second even, and so if we view that, then what will happen is that the arrival curve is really tiny, very small, okay, and the service curve is like so. We'll just ignore those tiny variations and just say they're continuous. In which case, we can say the arrival curve is something like this, and the service curve is something like that, okay? And these are both continuous functions of time, okay? And this allows us to view this gap over here as the delay of this particular, of this request over here, and then this is going to be the maximum queue length at that point in time over there. Okay, and so that's the continuous approximation to the discrete process that we have over here. Okay, you better wake up in the front row. Okay, so this continuous approximation is nice because we don't have to worry about any discontinuities, any jumps like this. Instead, we have this kind of nice, distribution of arrivals and so on over time. And for the purpose of this class, we're going to use the continuous approximation under the assumption that things are pretty small in time scale, so it can be approximated as a continuous function of time. Okay, so just to sum up then, we have over here on the x-axis we have time, and on the y-axis we have basically arrival and we have service, both. And that's the arrival curve A and that's the service curve S. Service curve is always below the arrival curve, and then we can view the rate, the slope at a particular point in time as the arrival rate at that time, and we can view the slope of this as the service rate over time, and then we can say that the arrival rate minus the service rate is the rate at which the queue grows, right? Because this over here is the gap, and that gap obviously is related to the difference in the slope. So if your arrival rate as being, okay, we'll talk about, okay, I want to make sure I use the same terminology as later. So let's say the buffer size is equal to x, and then let's say the arrival rate equals u, and the service rate equals w, then x dot equals u minus w. Okay, so rate at which the buffer grows. And of course, u and w are already going to be the derivatives of the arrival curve and the service curve at that point in time. So this is equal to sort of a dot, and this is equal to s dot. Okay, and these are a and s. So we have some arrival curve. The derivative is u, the service rate, the derivative is w, and then the buffer grows using this equation over here. And now we sort of have a mathematical model of the web server system, a very concise, simple model of the web server system, and we'll talk more about that in a bit. I want to just mention one more thing, and then we'll take a break, which is that let's view the system, sort of the whole system, a bit more carefully. We have some client over here, which is like a web browser, and then over here we have the server, the web server, and it has some queue, and we always draw queues like this. It's like that's a server and that's a queue. It's like these things from like a pile of plates, sideways, and that's going over here, and that's x. So all this is well and good. The two issues that the client has. First is that client doesn't know the size of the buffer, right? If the buffer is very full, the client sends a request, it may get dropped. That's not a good thing to happen. And second, the client doesn't know how long it's going to take for the queue to empty either, because each request for the web server takes different amounts in time, right? And the reason is because the web server has to do different amounts of work, right? If somebody says on a website, a Google search, it searches for a keyword that is very rare, very few people have used it, maybe it takes a long time, maybe if it's a popular keyword, it's easy to fetch. It's variable amount of time, but the client doesn't know it. So what does the client want to do? A client wants to send in a request rate. Okay, so for now we assume that the client is sending multiple requests to the queue one after the other. The client wants to send a request at a rate. If it's very slow, what's going to happen is the queue is going to drain. Web server is sitting there, it's got work to do, but the client can't give it any work, so you waste time. And on the other hand, if you send it too fast, the buffer fills up, you drop the request. So what the client wants to do is to send it at a rate fast enough so that it keeps the web server active but not too fast. Okay, and that becomes the control system over here. So in this case, the input, this is the client wants to choose a rate, or rather I should say, client wants to, controller wants to choose a rate such that the web server doesn't drop packets, and by measure, but we haven't put in any feedback, right? We haven't put any feedback over here. And so in the real web server system, we don't really have feedback. Okay, we don't have explicit feedback, but for the sake of exposition, we're going to assume that there is a feedback channel, and we're giving what we're going to do is we're going to find the buffer occupancy level. Is going to be given back to the client. Okay, and that's basically this is obviously not true. Okay, this would mean somehow that when you do a web request, you get back a message that says my buffer has so much capacity. And the reason we don't do it today is because the buffer capacity changes so fast. By the time you send that response back, it's already outdated. But we're assuming the instantaneous feedback, so we're ignoring the speed of light, and we get back the buffer occupancy. Let's try and look at that in terms of this model over here, and I think we'll get a good idea of what it is we're trying to do over here. So I'm actually making a couple of implicit assumptions in that web server model just to make life simple. The first one is that I'm assuming that the client, this one client, is actually generating all the load. Of course, that's not true. We're going to have hundreds of thousands of clients, millions of clients who are jointly going to generate the load for the web server, right? So we're assuming it's a single client. Okay, which is not the case. And the second thing I'm assuming is that there's the buffer occupancy level is being fed back to the client so that it can use this information in controlling the rate. Again, that's not something we actually have today. If you go back over here, what we have then is this. So the reference input, okay, so let me come to the reference input. So what is the reference input going to be in this system? Again, remember we're trying to model it, right? There are many different things you could have for the reference input, but I'm going to choose a particular one, and I'll explain why it is. And it's not the intuitive thing that you would think of. And the reference input is, and I'm going to choose as the set point for the buffer. So how big, at what value you want the buffer to be. Now, this is not obvious that you want to choose this, and the reason is because why would you want to have a buffer in the first place, right? Why would you want to have some amount of requests waiting in the queue? Because every request in the queue means delay, right? So if I have, let's say I set the set point to 1,000 requests, then on average I want to maintain 1,000 requests in the queue at all points in time. Why would I do that? Because that's going to add delay for every request that has come in, wait for 1,000 requests ahead of it, and then get served. That adds delay. The reason is because the web server's service rate is unpredictable, okay? And if the service is unpredictable, what that means is that there are going to be periods in time where the web server suddenly has capacity, suddenly it has the ability to serve requests. If the set point is low, let's say 0, okay, or then what happens is the web server is going to have additional capacity, but there's no work to fill it. And if there's no work to fill it, what's going to happen is that we're going to waste the server capacity, okay? And so that unpredictability is always going to be there, and we can get rid of it by choosing a set point which is non-zero. And by doing that, what happens is that to the extent that there is some work to be done and there is a delay in the feedback, we are able to actually use that capacity over there. All right. So that's the reason why the set point is non-zero. Now the problem is that the set point can't be too low or too high. If it's too high, we're going to add delay to everybody for no good reason. And if it's too low, we're going to waste the web server's availability. And so consequently, what we're going to do is that we're going to make that a reference input over here, which is the set point. Which means that we say, okay, if you want to be some user who really hates delay, fine. Waste the web server capacity, set the set point to be 0, that's fine. On the other hand, if you're a user or you're a system designer, that where the set point, where you really care about not wasting capacity, you don't care about delay, you can set the set point to be high. So this becomes what's called a control knob or a tuning knob. Okay, this is a very important thing to have. Okay, it says change the overall behavior of the system can be changed with just one single parameter. Okay, you just change the control knob, and the system will do whatever is required to meet that knob. Okay, and this control knob becomes a set point, and that allows us to do what's called a trade-off. You can choose to have higher delay and no wasted web server capacity, or you can have low delay and wasted web server capacity. So you can choose where you want to be in what's called the operating regime. Okay, and this is a typical thing we do whenever we design a system. We have a trade-off. You can have more of this and less of that, and more of that and less of this. What do we do? The answer is, okay, we'll give the user a knob. They choose the knob where they want it to be, and based on that, things are going to work out fine. For example, if you have a laptop, like your Mac over here, it says, do you want high performance and low battery life, or you want low performance and high battery life? You choose. We don't know, right? So what you do is you have a control knob, you choose that value, and then after that, magic happens so that the particular trade-off that the user wants is met. And this again is a typical thing we do in a system design, is that we choose a control knob. You want to make the control knob as intuitive as possible, right? But once the control knob is set, the system is going to work hard to try and meet it. So that's the input, the set point. The controller is choosing, this one over here is going to be the rate of sending requests. Okay, now what's the disturbance? Here the disturbance is kind of funny. This disturbance is funny because we are saying that the buffer is changing, the buffer set point is changing despite a particular rate of request. So why is that? That's because the service rate is changing over time. So the variation in the service rate is the disturbance. We're modeling that as a disturbance. Okay. In fact, we can go further. We can just say the service rate itself is a disturbance. Okay. And that's kind of a funny thing to do, but it works out just fine. Okay. So we can model the service rate itself as W. That's why I said the service rate is W. The service rate W is actually a disturbance over here, W, the same W. Okay, so we have, in fact, then a system where it's only disturbance. There's nothing but disturbance. The whole process is a disturbance process, W, and what the client is trying to do is to choose to be at a particular set point despite continuous disturbances all over time, or at all points in time, and that's basically what we're doing over here. Yeah?
For a given arrival curve, the web server has to be the same amount of work no matter what the set point is, right?
That's correct.
So why would you want the set point to be higher? Wouldn't that just slow down the rate at which it completes the work?
The arrival, so the thing is that although the amount of work that needs to be done is deterministic, as you said, however, the client doesn't know what that amount of work to be done is at any point in time. So if I take this point in time, right, the client has set this many arrivals, right? It doesn't know whether the service curve is here or it's going to be like that. It doesn't know what the future is. It only knows what happened so far. It can have some expectation of the service rate, but it doesn't know what the service rate is exactly. So it's going to say, okay, just in case I made a mistake, I'm going to have a larger set point, and then if the service rate, if the services take less time than I anticipated, right, then I'm going to have work for it to do. That's why you choose a larger set point. Okay. Any other? But the same exact logic applies to a router. Where if you have a router and you have some output queue, some of the output queue is going to be devoted to your traffic, and some is going to for somebody else's traffic, right? You don't know what anybody else's traffic is, so you're going to say, okay, if I choose this set point, even if their traffic goes away, I'll still be able to give work. So it's a very common thing we use all over the place to have a set point that is non-zero. But we don't know what value to use. Yeah?
So here the client is the controller, it's part of the system, right?
That's right. The client, when I say client, I mean the controller aspect of the client. So obviously the client is rendering the image and stuff like that, but we're not interested in that. It's just the rate control, request rate control. Any other questions? So what we're doing over here is that we are modeling the disturbance, the service rate as a disturbance, and then so then after that the plant is the web server, and then the measurement is measuring the actual buffer occupancy, the x, which is buffer occupancy. And the error is, of course, the difference between the measured occupancy rate and the set point that we chose. And that difference is the error. So if the error is large, okay, positive, it means that the buffer is much larger than we want it to be, so we lower our rate. And if the error is negative, we say, okay, we have to increase our rate. And so we're trying to, even though the service rate is changing all the time, hopefully what will happen is that the buffer occupancy, so this is the buffer occupancy versus time. Let us say, with any luck, if R is over here, we'll go above and below, but on average, we will be tracking it. We'll never go too far away from the reference set point for the buffer occupancy. That's what we'd like to do with this control. And we do that because we can do that because we have this feedback, and we're assuming there's only one client which is doing all the load. If there are more clients, or if you don't get feedback, then it's a different problem. And this is a modeling thing. Okay, so I've talked about these two, and I've taken more time than I anticipated. So I know there was a question on power and effort. So keep it, and then hopefully next time I'll pick that up, and we'll continue with the general approach to modeling and the mathematical models on Wednesday. Okay.